Так, дорогие коллеги, мы
Dear colleagues, as we continue, the next presentation will be made by Professor Esteban Zimányi from Brussels University.
To introduce our work we have been doing on the last couple of years about MobilityDB, which is a PostgreSQL and PostGIS extension for mobility data management. So first of all, what is mobility data management? We all have mobile phones that are continuously generating triples of time, location, meaning latitude and longitude. This stream of triples is continuously arriving either to our mobile telephone companies, or even, for example, if you are using certain operating systems, you are using, for example, sending this information to Google. So this is a continuous stream of data that can be arbitrarily huge. And then, but somehow, in order to have efficient management on that stream of data, we have to construct trajectories out of that. So depending on application requirements, we may not need to collect all the intermediate points within the stream, and then we can decide, for example, that only reduce the data sets by constructing these trajectories. As you can see there, we have transformed the initial triples into full trajectories, where, for example, you see there you have the point, which is already a PostGIS point with latitude and longitude, and associated to each of these points we have a timestamp. So basically, from this on, a trajectory is just a sequence of locations in space associated with a timestamp. Typically, as you see in the first two columns, we have an identifier of the object, and in addition, so for example, myself or a particular car. And after that, we can even decide, depending of the application requirements, for a single moving object, a person or a car or an animal, decide how to split the different trajectories of this moving object into different trips. But all this is application dependent. But we also need somehow to process this mobility data. In particular, we would like to know what is the speed of this particular moving object. And then, for example, starting from this data set, we can say that the speed of this object, and then for expressing this, we need to have a temporal number or a temporal float that basically it's trying to associate to each point in time the particular speed at which this object is moving. So then, in addition to moving points, we have also moving floats, but also we need to specify, for example, whether at a particular point in time there is a particular predicate is true. So, for example, here I'm asking whether it is true that the speed of this particular object is bigger than 19 kilometers per hour. So again, we need another temporal type, which is temporal Boolean, to express this kind of information about moving objects. And finally, we need also to consider other kinds of events. These are instantaneous events. If, for example, you are looking at accidents, an accident is an instantaneous event that occurs at a particular location at a particular timestamp. So if we want to to store this information in the database, we need to be able to also store this kind of instantaneous events. Or if you think about, for example, Foursquare check-ins, we need not only to have an instantaneous event, but a sequence of, or a set of instantaneous events, for example, the Foursquare check-ins. And then for a single object, you can associate a set of location and couples of locations and time. So now, so after this introduction, what is MobilityDB? So it's a mainstream moving object databases that builds on PostgreSQL and PostGIS. It is developed by a team at my university, Université Libre de Bruxelles, which is, by the way, the location where the last weekend it was located, FOSDEM, the great open source congress. It's meant to be open source. We are finalizing this to deliver the open source community. And what is important, it is also we are looking up and they're implementing all the relevant OGC, Open Geospatial Consortium standards, and in particular the OGC Moving Features Access, which is an evolving, or I mean, it's a beginning standard that is beginning to appear. There are many problems in this standard. We followed as much as we could this moving feature access standard, but nevertheless, sometimes we need to deviate from the standard, or even more, add the features that were not even considered into the standard. So let's have a quick example, and it is an example based on a real use case. For example, we started a research project with the city of Brussels, and in which we are accumulating all vehicle for the public transportation company, buses, metro, tramways, all the public transportations means in the city. We are collecting the data from these buses. Suppose that we have this table bus with a line number, for example, number 71 going from here to there. And then for each of these line numbers, we have several trips that a particular bus can be doing across this line. And finally, we store the trajectory of this bus into this type, which is a new type, temporal points. But as you can imagine, in the same way as in PostGIS, we have two data type, geometry for planar geometry and geography for round earth geometry. So here we have also two temporal points, temporal geometric points. In this case, it is a point using the spatial coordinate system 3812, which is the coordinate system for Brussels. But we can also have a temporal geography point for geographies. And then suppose that in addition we have another table which is point of interest. And this is a traditional PostGIS table in which we have the name of a place and then the location of this place, which is a geometry. And we want to list the bus lines that traverse a particular place, which is called Place Louise. So we go in our tool. We select first the location of Place Louise. We obtain the geometry out of that, and then we do the intersection of the moving geometry of a bus with the fixed static location of this Place Louise. Out of that, we obtain all the trips that traversed this particular. So here we are using an extension of the intersects predicates in PostGIS, and so in the first argument is a moving geometry, a moving point, and the second argument is a static geometry. In particular, we also took took into account indexes, and then, for example, intersects predicate, intersects function here is index supported. So it is, for example, an automatic call for these overlaps operators that performs a bounding box index filtering. Now, let's go a little bit more with trying to do queries about this data set. So now suppose we have a table network that defines the route that every line number should take. So now we have to investigate which are the trips that deviated from their line routes. So we have the two table, bus, which is a moving geometry, and network, which is a fixed geometry. We do a join of the two tables based on the line number, and then we do a routing of a buffer of 20 meters of the route of the route that is supposed to take a bus. And if it is not the case, if this buffering route contains the trip, we can easily see that the bus deviated from their planned route because, for example, an accident, because, for example, a demonstration. So with this query, we can define which are the trips that deviated from their planned route. We have also implemented aggregation functions on top of that. So suppose that we want to have the total distance per week traveled by buses. So we have a predicate, for example, which a function which is start timestamp of the trip, which gives the starting point of the history of a particular moving point. We obtain the week of this timestamp, and then we do the group by of the trips according to the week. For each trip, we compute the length of the trip. So this is obtaining a float associated to this moving point, and then we apply the traditional sum operator to do the aggregation. Now let's have a temporal aggregation. Suppose that instead you need to have the cumulative distance that traveled by a bus during each week. Here we don't need, as in the previous case, to a single float. We need to have, for each bus, we have to compute a temporal float that computes for example, the cumulative length of each trip. So this is the function cumulative length that obtained that. And out of that, we have a temporal sum that has all these temporal floats and have at each point in time associate the sum of all the cumulative lengths of all the trips. Here in the graph, we can see, for example, that in 3 days, during the night time, the bus are stopped, so the cumulative length stays static, and then at 8 o'clock in the morning again, or 6 a.m. in the morning, the bus continue to have add the cumulative length, and the next night again, the bus are stopped. And then spatio-temporal joins, for example. Suppose that we have a table which is stops, which is only the location of the different stops of our public transportation network. And then we need to have all switching or transit possibilities, meaning I am in a stop in the transportation network, I can change to another line, to another bus. So for this, I have to first compute in a temporary table all the stops, which is simply a union of the geometries of the stops. Then project at the second bus stop. So we project the route of a particular bus, and then we only keep the parts of this trajectory that are intersecting a particular geometry, and this particular geometry is one of the possible stops of the network. And then out of that, we have to find two stops, two bus stops, a bus A and a bus B, such that they are different, and then they overlaps in both the space and time. That means that at the same time the two buses are in the same place, and so the user can switch from one bus to another. This is the temporal overlaps predicates, and finally the ever equal operators. So temporal overlaps basically is telling me as a result a temporal Boolean, whether it is yes the case at this point in time there is a possible combination between the two buses, and then from this temporal Boolean I can ask whether sometime in this temporal Boolean it takes the value true. In that case, at least there is one possibility for switching from one bus A to the bus B. So after this small introduction of the capabilities of MobilityDB, let's have a little bit more in detail the various components. First of all, I will introduce time types. So time types, in addition to the timestamp or timestamp TZ that we have in traditional PostgreSQL, we needed to add 3 additional time types. The first one is period, which is exactly the same as TS, TZ range available in PostgreSQL. The problem that we have when the first implementation of MobilityDB with TS, TZ range, it was not performing well, in particular because it is of variable length. So by just replicating the basic idea of TS, TZ range, but for period, we have an improved performance. And then in addition, we don't need to have empty periods or infinite bounds for our temporal types. In addition to that, we have a timestamp set. You remember these 4 square check-ins. I need to have a set of timestamps as a possible data type. And I also need a period set, which represents a set of disjoint period values. And out of these 3 data types, we have to have functions and operators and indexing for that. So we have, for example, obtained the third timestamp of a particular period set, or operators for B3, for overlapping, for manipulating periods. For example, here we have 1 period minus 1 period. The result is a period set, since there is a hole between the two. And of course, we provide gist and SPGIST indexes for these time types. Now let's go to our temporal types. Temporal types, currently they are temporal integer, temporal float, temporal boolean, temporal text, and as I explained, temporal points, but in the geometry version and in the geography versions. And as I have already said, each of these types come in 4 possible durations. Either we store an instant, or an instant set, or a sequence set. And then, for example, we can do something like this: create a table department, department number, department name, and we keep the history of the number of employees of this department with a temporal integer. Or we have a flights, and we have a flight, and when we have a geography point with the 4326. And here for flights, we have to take into account that we have also need a 3rd dimension for the point Z. And for example, trips, this is the one we have seen. We have a car ID, integer for the trip ID, and a geometry point for a trip. As you have seen, we have type modifiers. In the case of trips, the trip there's a temporal geometry point, so we don't specify neither the temporal, whether it is a sequence or a sequence set or a period. So it is, we can have whatever kind of duration, whatever kind, either point or point Z, or whatever kind of spatial or SRID. So in the same way as when you specify nothing in a column in PostGIS, you can have whatever type of geometry in PostGIS. And then we can have, for example, a way to insert the values into this table. For the first trip of car ID 10, and we say this is the location of the trips of this the car going from point 00 to point 20 to point 21. One question that we ask at ourselves, whether we can use PostGIS trajectories. So in PostGIS, there are a few functions for representing time using the M dimension in PostGIS. So basically, why don't we use line string M? Typically, the problem is that the measure M is not designed to specifically represent time. So we cannot assume total ordering. And because of that, this prevents an efficient implementation, because, for example, you cannot assume that the times is always increasing. And, for example, the essential feature for obtaining performance is binary search. And this is not possible for doing in PostGIS trajectories. But we have seen also, we need also temporal numbers, temporal integers, temporal booleans, temporal string. And then this is why we implemented all these data types ourselves. So one question, how to generalize operations from PostGIS, which are static geometries, to temporal geometries. This is called lifting. Lifting is basically when you have a function like st-intersects, which is the traditional PostGIS functions, that takes two arguments, a geometry and a second geometry, and results in a Boolean value. Lifting means that as soon as one of the arguments is, one or both arguments of the function is temporal, then the resulting is also temporal. So suppose that this is the moving car that is going that. This is one part of the central of Brussels. So we are asking whether this moving car intersects this particular geometry. So it will be say yes, 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 no, no, sorry, no, 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 yes, entering into the geometry. As soon as it goes out of the geometry, it says no, no. So basically, lifting is applying the traditional st-intersects at each instant of the line of the lifetime of this object. Of course, this is from a conceptual perspective, but we have to somehow optimize that. We have to basically determine that to the left, during this period of time, nothing changed, so I have to pick an arbitrary point during this period of time and say, no, it is no. At the instant I am entering in the geometry, I have to verify, compute the st-intersects, or it could be st within or whatever. So the entrance point can be yes or no, depending on which operator I'm sending to. I am delegating to PostGIS. In the inside, I take an arbitrary point. At the exit point, I have to again ask again to PostGIS the same st-intersects, and then one arbitrary point at the exit. So basically, the idea lifting is you have to apply the same traditional operator to each point in time. What is important here is I fully depend on PostGIS. I delegate all the spatial manipulation to PostGIS, and I only taking care of the temporal aspects. And then we developed generic methods for efficiently doing this lifting of functions. So, example, we have constructor functions to create points. In this case, I create a point of an instant or a sequence duration. I have accessor functions. I have spatio-temporal functions. For example, I would like to have the time-weighted centroid. In the same way, we can compute a time-weighted average. So when you are computing time-weighted aggregation function, the more you stay at a point, the more this point is taken into account for doing your average or for doing your centroid. And for example, this is one example for nearest approach distance. We have a moving point and we have a geometry, and then we can say, give me the smallest distance between the two objects ever. And we have this projection function. We can, the example that we have seen already, we have a moving point here, we have a polygon, a geometry, and we are wanting to restrict only this part of the, instead of analyzing the full history of the trajectory, I only want to analyze the history while this was, there is an intersection with this geometry. We have the same way that we have projection at geometry, we will need minus geometry. We have comparison functions for example, the traditional B3. Temporal comparison, it means instead of having a temporal, a single Boolean, we have as a result a temporal Boolean for stating, is it true that the speed of this car is less than 60 kilometers per hour, for example. We have temporal operators, we have bounding box, distance, spatial relationship, we have seen that. We have Boolean operators like intersects, meaning does this object ever intersects this other object? And the temporal intersect that says at each point in time, give me whether this object is currently at this point intersecting the other object. GIST and SPGIST indexes are supported. For this, as usual, we use a bounding box. And depending on the type, we have 1D, 2D, or 4D bounding box. For example, for Boolean and text, we don't need to, we only take into account time. For integer or float, we use boxes to have in the one dimension the value, the bounding box of the value, and the other dimension, the bounding box of the timestamp. And for geometric or geographic point, we have 4D because we have 3D already for the XYZ, and the fourth dimension for the time. And then we have the index. These indexes, of course, accelerate queries for the operators, whether it is for example, what is important here is that we defined polymorphic indexes in the sense that sometimes some systems need, for example, one spatial-only index, a temporal-only index, and spatio-temporal index. You have to have three types of index on the same column to verify whether this is before this timestamp, or whether it intersect this geometry, or whether two moving objects intersect. So we have a polymorphic nature, and we have a single index, and then depending on the arguments, how many dimensions are shared between the column and between the argument that is, then we determine whether we need to take only into account time, or only space, or both time and space. Now, SPGIST indexes. SPGIST indexes, as you may know, have a strong requirement that the values cannot intersect. Overlap, sorry. The values that to be indexed cannot intersect. And then because of that, we reuse an approach developed for SPGIST indexed in the box type, which is coming in the distribution of PostGIS. So basically we have, the distribution of PostgreSQL. So basically we have to, for a period, we have to transform a period, which is a one-dimensional time dimension, we have to put 2 dimensions. For example, for temporal floats, we need to transform the bounding box in a 4D, or for a temporal point, we have to use 8D. So we developed this as, again, I probably developed it by one of the guys here from Postgres Pro that is in the PostgreSQL distribution. We extended that, and finally we realized that SPGIS indexes were not available for the traditional PostGIS distribution. We downgraded our solution, and then proposed patches for 2D and 3D geometry, which was already delivered in 2.5 of PostGIS, and in the next version of 3.0, we have the n-dimensional SPGIS indexes that will be delivered in the main distribution of PostGIS. We have aggregation functions, as we have seen. We have regular aggregation functions, we have temporal aggregation functions, and we have sliding window aggregation functions. This sliding window parameter needs an additional parameter, which is an interval. So, for example, give me the speed of the trip, but take into account also the last 10 minutes to somehow take into account the history or the evolution for the aggregation. We are able to do parallel execution. So, for example, in this query, I'm computing how many cars were active at each period in this table period. So we can see here we have implemented the features available since PostGIS 10 to do parallel aggregation, and then this is an example of and explains how these different workers are basically doing in parallel the aggregation, and then the gather merge obtains the final result. We also take into account partitioning, so it's a feature for PG11. So suppose that I have these table trips, and as you can imagine, this table trips is always increasing in size. So I want to partition the trips by day. So I have one partition for each day, and out of this, I can have the same query in which all the different partitions are taken into account in parallel for doing the aggregation. So we have 3D temporal points, as again, we deliver all the spatial information to PostGIS. So as every function that is 3D in PostGIS, we can generalize it for the temporal part. And so to wrap up, so where we are now, so we started our development a couple of years ago at ULB. There are currently 2,000 functions, 62 lines of C code, 19,000 lines of SQL, and 20,000 lines of regression test. We have very nice results for robustness, performance, and benchmarking with respect to PostGIS trajectories and with respect to Segundo, which is a traditional research tool for moving objects. We are currently finalizing the planner statistics and selectivity function. These are tricky. The team that is working on them is, I have a meeting next week to finalize this issue. We are planning to move it to GitHub soon, and then it will be delivered open source as it is ready. And we have already exploring several extensions, in particular network constraint trajectory is an important one, because until now the model is a free space model which going from one point to another. But if you are in a transportation network, if you are doing the distance between 2 points, this is not the right distance. The distance should be through the road network. And for this we need to use network constraint trajectories, and we are already exploring this with PG routing. So there is already a demo in which, for example, we loaded the Berlin mode, which is a traditional benchmark for moving object databases. And then all this data is there and you can play around with these queries. And so thank you for listening. I'm here for your question.
Thank you. Very interesting. And I at least participated in GIST and SPGIST. So could you compare performance of them?
Yes, this is an interesting question. For the moment, we have mainly used synthetic data. Obtaining real data is tricky, so this is why I needed to launch a project with a transportation company, public transportation company, to obtain real data. Out of this data, we are beginning to do the test GIST versus SPGIST. On synthetic data, meaning random data, SPGIST is performing better. So, I mean,
That's cool.
No, I really like, this is why I push somehow PostGIS to have SPGIST indexes, because and it was significantly faster, SPGIST indexes. So, and this trick, maybe it was yourself that did this trick for transforming 2D onto 4D.
It's not mine idea but I participated in that.
So it has a great idea, that's amazing. Thank you for this idea.
Сейчас микрофон вам донесут, секундочку.
You'll get the microphone in a minute.
Points one by one to the...
This is a very nice question. So for the moment, this extension, we are working in historical data. So we are receiving, for example, the last 3 years of this transportation company, and then we do analytics on top of that. If you are doing real time, you need a solution like, I don't remember, Ivan discussed it yesterday with timescale DB. So we are in the process of exploring ingesting real-time data through timescale DB. Is that your
in your
question?
system, will it be much better to construct the whole road and only then convert to your type?
I mean, we need what is called a lambda architecture. At the speed layer, we need to continuously get the updates and construct the trajectory, clean the trajectory because of the GPS errors, map matching. So this is a very complex process. When this is clean, then we can pass the trajectory to the batch layer and then store it into MobilityDB. But for the moment, MobilityDB is only for historical data. All this pre-processing has been already done, but we are already exploring this pre-processing also.
And how it's actually stored? Is there any compression comparing to text representation of the type?
For the moment, we have not explored any compression, but for the moment, this is really like this: a PostGIS data type and a timestamp, and then sequence of that.
In binary value, yeah?
In a binary format. Yes?
1 second, please.
Thank you. And one more question about storing. For your track, you have several points. Each point is a separate PostGIS geometry type with own SRID, or you use line string and array of timestamps?
This is an alternative, two alternative possibility that we explore. Our experience is that this point associated to timestamp is easier to manipulate because most of the time you only need part of the history, and then this part of the history is already assembled immediately if you have a geometry, and in another part of the memory you have an array of timestamps. When you are slicing this trajectory, you have to assemble after that so it takes time. So just like this is exactly what we experience the best performance.
Okay, thank you.
Thank you for your time, for your question. Just I forget to mention, of course I was not alone doing this exercise. Our team in Brussels is I'm not the only person behind, but I would like to thank Darafay, with whom we have been very lengthy discussion for 1 year and a half. Many of these ideas from you see me here now are a result of our heavy discussion with Darafay. Thank you for that.
Thank you very much. It's time.
Thank you.
Thank you. У нас перерыв 5 минут до следующего доклада.
We have a 10-minute break before the next presentation, and please remember that the flip chart is near the stand, so please register for the short reports and also leave your opinions on the website of the conference.